Hi, today we're covering section 1.2 for college algebra. And what we're going to do today that's different from section 1.1 is instead of visualizing one variable data, we're going to visualize two variables at a time. And the way we're going to do that is with scatter plots. So we want to talk about what a scatter plot is. So you're visualizing one, you're seeing one right down here. This right here is a scatter plot. And we're going to talk about it here in a second. But the definition itself of a scatter plot is a graph of ordered pairs. So your ordered pairs are the pairs with an X and a Y. So they always look like this. You are always going to have an X-axis and a Y-axis on this graph. And it shows the relationship between two variables because you're seeing those two variables right here, your X variable and then your Y variable. So key things to remember here is that on a graph, your horizontal axis down here is your x-axis, and your vertical axis is your y-axis. So here, we can see that on our x-axis, we have the variable year. So we have the variable x here for year, and our y variable is on the y-axis here, which is median age in years. So this particular scatter plot looks at the median age of the US population over time. So it's looking at two variables. How does time changing affect the median age of the US population? Okay, so or how is the median age of the US population changing over time? And when we look at these numbers over here in the table, we can obviously tell some things like, okay, it's going up over these years, it goes down a little bit here, and then it continues to go up. But visualizing them in a scatter plot, we get to see comparisons between those increases, right? We get to see that the increase from between these 2 years is about the same as the increase here. Then it goes up a little bit more, up a little bit steeper, up a little bit steeper, and so on. We see those drops a little bit more clearly and what happens around them. So scatter plots are a great way to visualize how two variables are related. Okay, so what we want to do today, more than just understand what a scatter plot is and how to make one, is to analyze a scatter plot. Talk about all those changes going on. What are the key points that we want to look for in a scatter plot in order to talk about how the two variables are related? So let's look at those key points. What would some key points be that we would definitely want to point out? So as a rule of thumb, maxes or mins are always key points. So where was it the lowest? Where did it end up the highest? And more than just where is there a highest and lowest point, for this graph, that would be at the beginning and at the end, we also want to talk about things like changes from increasing to decreasing. Those are always major points of interest. What happened there, right? We see a trend and then all of a sudden the trend changes. And we want to point those out and talk about those changes. And often we'll look into seeing why that change occurred. So where does it change from increasing to decreasing or vice versa? So where does it change from decreasing to increasing? When we see those changes in the trends, we definitely want to point those out as key points. Okay, so as I was saying here, we have about 3 key points happening in this graph. We have a minimum, which happens in that year 1850. We had that minimum, that first data point we were looking at. So we like to talk about that. There's a minimum in 1850 at a median age of 18.9 years old. And we know that exact amount because we have the table of values over here. If we just had the graph, that would be okay, but we'd have to estimate where that data point was at. We also have a maximum. Our maximum is that last year we're looking at there, 2010, which is at 36.9 years old as a median age of the US population. And we have a change from increasing to decreasing that occurs. Okay, the trend goes back to increasing afterwards, but those are important points right there. So we're seeing that something happened between, looks like 1950 and 1970. Okay, we're seeing a change there in the trend. So by 1970, we've seen that change And by 1970, we saw that change from increasing to decreasing. Okay, so something's happening around 1970 that's causing that median age in the US to go down. Now, we're not going to go into the whys, but as someone was looking at this data, that's when they would start researching, okay, what's going on in these years? Or overall, why is overall the trend increasing? So that's the second thing we always want to look at with a graph. Not just the in-between parts, but also just overall. Is the graph increasing? Is it decreasing? Or is it doing neither of those things? Is it staying pretty constant overall? Okay, or is it some sort of combination, right? So some graphs we can see they'll go up and then go down the whole time afterwards, or vice versa. So it could be a little bit of a combination of those trends overall, depending on the shape that those points are making. And those things are really major things that we want to look at when looking at a scatter plot. And they're also the things that we want to make sure we point out when we talk about describing the overall trend between two variables. So given this scatter plot, if I want to create a summary, in your book they call it the 60-second summary. If I want to create this summary of what's going on, how median age of the US population is related to time, these are the things I want to point out. I want to point out the overall trend, and I want to point out these key points overall, so that I can catch some of the major things going on between these variables, okay? So this can have a lot of different looks, but the major part here is not to leave out too much detail, okay? So it would not be enough to say, overall the trend increased at one point, it decreased, and done. You want more detail there. So I'm gonna give you an example of a paragraph, a short paragraph that describes this scatter plot. Maybe pause and give yourself a shot at describing the overall trend and see if you get kind of close to what I'm thinking is a good paragraph to describe the overall trend. Okay, so mine would be something like this. I would say I would want to point out the years that we're looking at. So overall, we're looking at the years 1850 to 2010. So I would say something like from 1850 to 2010, the median age of the US population increased, because that was the overall trend, increased, and I'm going to actually go ahead and point out those increases. So increased from that minimum at 18.9 years old to that maximum at 36.9 years old. And you know, you're writing a paragraph here, so I should probably actually spell out years. I'm just used to writing notes, so I'm abbreviating. Okay, so from 1850 to 2010, the median age of the US increased from 18.9 years old to 36.9 years old. And then maybe I'd say like, however, there was a decrease from, let's see, it was from 1950 to 1970 from a median age of, let's see, in 1950 it was 30.2 years old to 28 years old. The trend returned to increasing. Whoops. After 1970. So again, you can say that in a million different ways. We all write, we all talk differently, right? But what I want to point out is the amount of detail I have here. I've pointed out specific years. I've pointed out specific ages, so I can tell overall how much it's increased. I know the overall trend was increasing. I know there was this point of interest though where we did see some decrease, and I know by how much it was. Now you're not going to be able to summarize the entire scatter plot. We don't know what happened in each year, and that's not the point. If we want to know what happened in each year, we would look at the actual scatter plot. These are just summaries. I want to point out those main points. You want to make sure you have the maxes, mins, overall trends, and any key points of interest. Okay, so every time I write this, it kind of turns out a little bit differently. Yours will not be verbatim this, but it should be something close, and it should have just about as much detail in it. Okay, your book also has some good examples of some other summaries of scatter plots. So we just want to understand scatter plots, how they work, how those points are related, and we also want to look into, okay, there's these cool times when two variables are related very, very closely. And in fact, if they're related perfectly, we can put an equation to that relation to describe the change. So more than just looking at the scatter plot, we can look at an equation that relates these two variables. So this is some made up data, but this is data that is perfectly related by an equation. So if you notice, all of these points make a perfect line. So there's actually an equation we could put to this data. It turns out that this data is related by y equaling 6,250x plus 1,140. Now, we have to use technology, at least as far as this class goes, to get that equation. So if it is perfectly relatable by an equation, that equation will be given to you. But equations are very powerful. So instead of having to look at this graph to tell, okay, about how many years of education would I have to have in order to make a median yearly income of a certain amount, I could just plug in that amount of education and get out that earnings. Very powerful. So I don't have to estimate it from a graph. I don't even have to create the graph. All I need is this one equation to describe what's going on and to know what the two variables mean, of course. All right, so in this particular case, education and median yearly earnings, as far as this data set goes, are perfectly related by this equation. So what we want to do now is just look more into these equations. How can we use these equations? How are they so powerful? First of all, the solutions of an equation mean that if I have an x, there's a y that comes out, right? Every time this equal sign is true. So the solution of an equation in two variables, x and y, and you again can call these two variables anything you want, we'll typically call them x and y, are just the ordered pairs that make the equation true. So it has to be that if I plug in x or if I plug in y, I get out the other variable exactly. So let's see how to figure out if something is a solution. So can you tell if the ordered pair 0, 1,140 is a solution of that equation that represents the scatter plot above? What would you do to figure out that it was a solution or not? Well, we have an x and we have a y value. So let's plug those into the equation. Our y value is 1,140. And our x value is 0. So I need to take that 6,250 times 0, because that's my x value, and add 1,140. And I'm asking myself, is that true? Is that equal sign, does it hold up? So what we need to do is simplify the right-hand side. Anything times 0 is 0. And if I add 0 to 1,140, I get 1,140. So I'm asking myself if that's true, and in the end, I can tell that that is true. So since the equal sign holds up, we have identified a solution of our equation. All right. The solution to that equation then has some meaning because those variables have meaning. We'll work on getting into that later on, but right now we're just focusing on the equations themselves. So maybe pause the video real quick and see if you can tell if this next one is a solution of the equation. And this one really points out how important it is that you plug the right variable into the right place. Notice we're working with the same two numbers, but they've switched spots. So now the x is 1140 and the y is 0. This is an entirely different question from the first one. So did you plug in 0 for y? And did you plug in 1140 for x? So that's what you're multiplying 6,050 by, 6,250 by. And right now, you can probably tell this over here is not going to equal 0, right? But you can go ahead and do that math. You'll end up with something like a very big number, right? If you take 6,250 times 1,140, you get 712,500, and then you're going to add some more to that. So we certainly know that those two things are not equal. So that means that this is not a solution to our equation. Is not a solution. Whereas at the top, this is a solution because the equal sign held true. Okay, this one's not a solution, this one is a solution. But most often we're not given a point, we're just given the equation and we want to find some solutions to that equation. And that tends to be a little bit harder because it ends up giving this open-ended question a little bit to it. If we want to just find any solution, well, we can tell that there's multiple solutions to this equation, right? The equation would be all the points on this graph. All the solutions would be any point I could find on that graph. So how do I find just any solution? I just want to find a solution. Well, the typical thing to do, because typically we have y by itself, is you want to pick any value you want for one variable. And we'll typically pick a value for x, but you could pick a value for y. So we're going to pick any unknown value we want for x. Then we're going to solve for the other variable. So if we picked the value for x, we're going to solve for y by putting whatever x we picked back into the equation. Okay? And if we're solving for any solution, we just want to make sure if we know a solution, we don't end up finding that same solution. So for example, in this problem, we want to find another solution to that same equation we were working with before. Now we know that 0, 1140 is a solution. So the only thing I wouldn't want to pick for x is 0 because I'll just find the same solution again. So pick anything other than 0 for x. You could pick decimals, you could pick fractions. I'm going to keep it simple and pick a whole number. I'm just going to pick x equals 5. Let's say I wanted to know, with 5 years of education after 8th grade, which is what that x variable meant, how much would the median earnings be? And y, I can solve for that because now I've picked a value for x, so that x in my equation is 5, and now I just have some numbers I need to simplify on the right-hand side to solve for y. 6,250 times 5 plus 1,140 ends up being 32,390. So I would figure out that my median earnings were 32,390, and I would know that the coordinate point 5, 32,390 is a solution, is another solution to my equation. Now again, I could have plugged in any x that I wanted. I could have plugged in 4, I could have plugged in 4.5, I could have plugged in 7. Now in this case, those decimals and fractions don't really make sense, right? Because in order to earn more, you'd have to have that full year of education. You'd have to have completed more education. But in some scenarios, those fractions and decimals make sense to look at. It really just depends on what your variables mean. But now what we know is how to find any solution to an equation. You just have to pick one variable and solve for the second variable. The last thing we want to talk about in section 1.2 is these graphs. So I did mention this before, but technically what a graph of an equation is a visual representation of the set of all the points that are solutions to the equation. You can see up here, there would be no way to list all the possible points. Right? If I could plug in anything for x I wanted here, I can't find all of those solutions. So we use graphs to visualize all of those solutions. So right here, we're seeing the graph of this equation. This one's a more complicated equation, and it looks like an ellipse. What I want to do is talk about the power of graphs versus the power of equations. So we just talked about the fact that equations are very powerful, right? It summarizes the relationship between two variables in this one simple line. I don't have to create a graph or anything. But graphs are also very powerful because I get to visualize all of the points on the graph. But graphs have their limitations too. So really, if we can get both of these things together, we're in really good shape. Because we can see here, if I just have the graph and I want to know the solution to this equation by just using the graph of 1y. So if I want to figure out the y coordinate when x is 1, you're going to see we're going to have a little bit of trouble. If I go to the x value of 1, so that would be right here, I'm looking for the y value. So that could be up here, or it could be down here. Okay, let's go with the positive version. Either way, when we're trying to estimate either of those points right there, y is hard to approximate. I'm going to erase that so we can see it a little bit better. We can see right there that it's somewhere above this line right here, a little bit above it, but what would that even be? So we can do things like look closer at the scale of the graph. So if you'll notice, there's 5 tick marks up to 1. So if you take 1 divided by 5, you'll see that each one of these tick marks is worth 0.2. That means this line right here is 0.8, and we're a little bit above it, maybe halfway in between that and 1. So I'm going to estimate that y value to be about 0.85. And we're just going to estimate that one. For right now, I'm just going to ignore the one down here. But you could have estimated that as well, and we'll see how we can get both of those answers actually by solving. But here, we've estimated it. But again, we don't know that exact value. It's not exactly halfway between. I'm just estimating that value. And it took some math to do it, right? We had to find the scale of the graph and things like that. Now, we're close, and we can visualize this equation really well using the graph. But what the equation allows us to do is get those exact values for solutions. So even though the equations make it hard to visualize the graph sometimes, like if you looked at this, you probably didn't know this was going to turn out to be an ellipse, right? But what it can do is give us that exact output that is the solution when x is 1. Because I can plug in x is 1 into that equation and solve for that one missing variable by just doing a little bit of algebra. So let's go ahead and do that. We've got 1 squared, which is 1, plus 4y squared equals 4. We want to get that y term by itself, so we're going to subtract 1 from each side. A little bit of algebra review here. All right, solving equations. When we want to solve for the y squared, we need to divide off by the 4. Y squared equals 3/4. And then to undo a square, we square root. So what we get here is that the exact answer is the square root of 3/4. And if you take the square root of 3/4 in your calculator, you will get about 0.86602, and so on. So we can see we were close when we guessed 0.85, but this is the exact answer down here. And the reason we're seeing 2 answers is that one is just a little bit of an algebra rule that you may have forgotten, which is that when you square root a variable like this, you always get plus or minus that solution down here. So that's why we're seeing 2 answers in our graph. All right, so equations are very powerful for giving exact solutions, but graphs are very powerful for summarizing that entire equation and giving us a visual. The 2 together are about as good as you can get. So that's about visualizing the relationship between 2 variables. We're always going to use graphs in these equations when we're able to in order to do that. Now, as we saw at the beginning, right, there was no equation that would have related these 2 variables. So sometimes we can only look at the graph. And that's when we're going to use the graph and some quick 60-second summaries in order to describe the relationship between those 2 variables. But when we can put an equation to it, we're going to be in very good shape. All right, so go ahead and go try that homework and come with questions. Thanks, guys.